Good afternoon, everyone. This is Zhiqiang Wang from Tencent. I'm excited to introduce our work, QDSR, accelerating layer 7 load balancing by direct server return with QUIC. This is joint work with Tsinghua University, Tencent, and Peng Laboratory. Generally, load balancing is a service that distributes traffic to multiple backend real servers and it provides an abstraction that multi-service server client as a whole. As a necessary infrastructure, service provider deploy load balancer to achieve high availability and prevent interruption caused by single node failure. Meanwhile, real server may be attacked and it will affect regular transaction. Load balancing could perform anti-attack strategy to prevent attack traffic arriving real server. Usually, load balancing is divided into layer 4 load balancing and layer 7 load balancing. Layer 7 load balancing and layer 4 load balancing are usually used together. Layer 4 load balancing is responsible for connection consistency. That is, the packets belonging to the same transport layer connection are forwarding to the same real server. It's not aware of the state of connection, but layer 7 load balancing supports more flexible content-based scheduling. It not only schedule requests in the same cluster, but can also schedule requests to another cluster. When the real server is a cache service, the load balancer usually needs to maintain sticky redirection. That is, requests to access the same resource need to be dispatched to the same real servers. As usage scenario increase, the role of layer 7 load balancer and real server are interchangeable. For example, when the request reaches the first server in the cluster, the server will query whether the resource is cached in the local disk. If it's, the server will return the resource immediately. If not, another server will be selected through a hash algorithm and it will return the resource. In this case, server can act as a load balancer and can also actually handle requests. Layer 7 load balancing has a lot of advantage. Content-based scheduling, fault-tolerant, and as a web application firewall to avoid attack. However, the disadvantage of traditional load balancing is redundant downlink forwarding, as shown in this figure. First, the client sends a request to the load balancer and it forwards request to real server A. Then real server A processes the request and generates response to the load balancer. Finally, the load balancer forwards the response to the client. The redundant downlink forwarding is additional performance overhead of the load balancer. It also increases transmission delay. Usually, the downlink traffic is much larger than the uplink traffic. Therefore, the redundant downlink forwarding traffic will increase bandwidth consumption. Over one is bandwidth fee. In LAN, such as data center, is congestion possibility. Direct server return is aimed to solve redundant downlink forwarding. As shown in this figure, the downlink response is directly sent to the client, bypass the load balancer. For layer 4 direct server return, because of stateless, the downlink packet easily bypass load balancer, like Linux virtual server direct routing model. However, it doesn't support content-based scheduling. For Layer-7 direct server return, like Prism, is achieved direct server return by serial TCP connection and TLS state handoff between Layer-7 load balancer and real server. The TCP connection state only handled by one server, so it doesn't support parallel scheduling. Therefore, it is not applicable to HTTP version 2 and QUIC. How to support direct server return in HTTP version 3? QUIC is a transport layer protocol of HTTP version 3, and one HTTP request corresponds to one QUIC stream, and different QUIC streams are parallel, and there is no head-of-line blocking. The challenge to achieve quick direct server return is how to migrate different QUIC streams to different real servers at the same time, and multiple real servers send HTTP response without affecting each other. We propose two-phase stream handoff to achieve parallel direct server return. The first is redirection phase, and the remaining is transmission phase, as shown in this figure. In redirection phase, load balancer selects one real server according to some strategy. After scheduling, it transfers QUIC stream state to the selected real server and use this stream directly response client. In the transmission phase, the real server sends a downstream response directly to the client, and the load balancer forwards control message from the client to different real servers. The transmission path is triangle. To perform QUIC stream handoff, there are some necessary states to be synchronized to the real server, including QUIC connection ID and its associated packet number space, QUIC stream ID and its flow control limitation, negotiated TLS key, client IP address and UDP port, and Layer-7 load balancer's IP address UDP port. Real server recovery forged QUIC connection and stream by these states without interaction with the client. After that, the real server can send a response directly to the client. In redirection phase, the real server may disable QDSR. Is compatible QDSR and traditional proxy-based scheme can coexist in one connection. The forged packet looks like it was sent by the load balancer, but is actually sent by the real server. How do real servers construct forged packets? As shown in this figure, response header and content are encapsulated as HTTP version 3 frame. HTTP version 3 frame will be split into QUIC stream frame. QUIC stream frame should be encrypted and encapsulated as QUIC packet. QUIC packet will be added with the forged IP address and UDP port. We utilize packet number space to isolate different real servers sending packets simultaneously. What is packet number space? Every QUIC packet must have a unique packet Every QUIC packet must have a unique packet number belonging to a packet number space, and it starts from there and increase. IETF QUIC only supports one application packet number space. One packet number space cannot support parallelly multiple senders because it will cause clients receive QUIC packet not in the order of packet number. In that case, the client's fast packet loss detection machine fails and replay packet tags are difficult to recognize. Therefore, we introduce individual packet number for every sender, like multipass to isolate transmission state of different sender. In transmission phase, the transmission path is triangular. The real server sends content to the client, and the client replies ACK frame to the load balancer, and the load balancer forwards the ACK frame to the real server. In this process, load balancer acts as a control center to coordinate multi-servers, including forwarding ACK frame, updating state when QUIC connection changed, and other control information. Real server acts as transparent real sender, is responsible for loss detection and retransmission, and performing congestion control. We implement QDSR with NGIX, Apache Traffic Server, and Lightspeed QUIC. And the evolution baseline is the traditional proxy-based scheme. The testbed is referred to this figure. Firstly, the bottleneck is the load balancer. We limited the load balancer workload with a single CPU core and provided enough real servers. The protocol between the load balancer and the real server is TCP. The concurrency is 8 QUIC connection and 8 stream multiplex pre-connection. The results show the size of request object increase. The source put gain also increase up to more than 10 times. The CPU bottleneck is different when different scheme and different request object size. For small request objects, the bottleneck is request processing. When request object size exceeding 60 kilobytes, the QPS decrease and relay consumption increase. As the size of request object increase, although the QPS decrease, the source put increase, so forwarding consumption also increase. In LAN evolution, we perform cross-synchronization to measure one-way delay, and the downlink one-way delay is significantly lower than proxy-based scheme, and the round trip time also benefits some from the direct path. For one end-to-end delay, we perform simulation experiments using Maha. This transaction benefits from topology of direct server return. For topology A, the direct path is not shorter than proxy path, so the gain is there. For topology B, the direct path is shorter than proxy path, so the long trim time gain 16 milliseconds. To sum up, in this work, we illustrate the significance of parallel direct server return for layer 7 load balancing, and we design QDSR to achieve parallel direct server return without damaging flexibility and scalability of layer 7 load balancing. And we implement QDSR, and our route is performance compared with the traditional proxy-based layer 7 load balancing. The results show that the performance is greatly improved. Please attention to our work, our future work. QUIC is the Rust QUIC library, and Tencent Yuan will support QDSR. Other detailed discussion can email me. Thanks.